Okay, I want you to imagine something for a second. Think about a seemingly impossible supermaterial. We're talking about a material that stays completely solid at room temperature, but somehow it can heal its own scratches. A material you could twist into a tight knot, but the moment you heat it up, it remembers its original shape and snaps right back. Now take it a step further. What if you could bring a solid block of this stuff onto a zero-gravity space station and 3D print complex, high-strength machine parts out of it without spilling even a single drop of liquid resin? I know, it sounds totally like science fiction. But today, we're actually going to look at the very real chemistry and engineering that's making this a reality.
Welcome to today's Explainer. If you're as fascinated by the absolute cutting edge of materials science as we are, well, you're in exactly the right place. Today, we're diving into this awesome convergence of advanced polymer science and real-world engineering. We are looking at a class of materials that are literally rewriting the rules of what plastics and rubbers can do. And in the process, they're solving some massive, long-standing engineering headaches. So let's take a quick look at our roadmap for today. We'll start by meeting the Vitrimer. Then we'll get into testing with DMA, tackle the damping challenge, explore the layered composite solution, and finally wrap up with some really cool additive manufacturing breakthroughs. All right, kicking things off with Section 1, Meet the Vitrimer. So what exactly is a Vitrimer? To really grasp the potential of what we're talking about today, we need to understand that this is a material that just flat out refuses to be boxed into our traditional polymer categories. It is defined by something called dynamic reversible links right inside its chemical network. Think of it like this. Vitrimers live right in the Goldilocks zone of materials science. Normally, you've got thermoplastics. Think of a plastic water bottle. You heat it up, it melts, it flows. On the flip side, you have thermosets, like epoxy resin. Once a thermoset cures, it's locked in permanently. You literally have to burn it before it'll ever melt again. Well, Vitrimers sit right smack in the middle. They possess a reversible network, so they have the tough permanence and structural integrity of a thermoset, but if you apply the right stimulus, like a blast of heat, those chemical links just temporarily let go, allowing you to completely reshape the material. The really crucial takeaway here is that these dynamic networks give the material genuine superpowers. Because the bonds can actually break and reform, a Vitrimer can self-heal its own microfractures. It also features this incredible shape memory effect. This means you can heat it up to program a new permanent shape, and no matter how much you twist or deform it later, it will inherently remember that form and revert right back to it. You can completely reshape it at higher temperatures, yet it remains remarkably solid, stable, and ready to work at room temperature. Moving right along to Section 2, testing with DMA. Now, to actually quantify these superpowers, researchers rely on something called dynamic mechanical analysis, or DMA. It's essentially the gold standard for testing viscoelastic materials. The way it works is, researchers put a sample into a machine, apply a vibrating mechanical force to it, and then slowly ramp up the heat. The DMA tracks how the material's behavior wildly shifts as it passes through different thermal states, like hitting its glass transition or its melting point. Let's break that testing data down into plain English. The first metric is the storage modulus. Think of this as the bounce. It measures the material's elastic, solid-like ability to store energy. Next, we have the loss modulus. Think of this as the flow, measuring the material's viscous, liquid-like ability to dissipate energy as heat. And finally, there's tan delta. This is just a simple ratio, the viscous response divided by the elastic response. Basically, it represents the material's overall shock absorption. Listen, if you take away just one single metric from the testing section, it absolutely needs to be tan delta. Why? Because tan delta dictates exactly how well a material can absorb energy and dampen vibration. A high tan delta means the material is just phenomenal at absorbing shocks, which, as you can imagine, is exactly what you want if you're trying to build heavy-duty engine mounts, bridge dampeners, or aerospace shock absorbers.
Which brings us to Section 3, the damping challenge.
Here is the massive headache for engineers. Materials typically only absorb shock well at very specific, narrow temperature bands. Usually it happens right as they're melting or transitioning from glassy to rubbery. On a chart, it looks like this sharp, fleeting peak. But think about a car engine, or heavy industrial machinery, or a spacecraft. They go through extreme, wide-ranging temperature swings while they're running. If your damping material only works at exactly 60 degrees Celsius, well, it's completely useless when the engine is freezing cold on startup or running incredibly hot on the highway. What engineers desperately need is a tan delta plateau. We need a high, flat line of shock absorption that stays steady across a wide range of temperatures. But engineering a single material to actually do that, it's incredibly difficult.
So how do we fix it? Enter Section 4, the layered composite solution.
Rather than trying to invent one impossible magic molecule, researchers came up with a really elegant workaround, a composite sandwich. They took a highly viscous, pure Vitrimer core and sandwiched it directly between two layers of highly stretchable elastic polyester fabric, essentially a kind of spandex. This physical architecture literally forces the two different materials to team up. Remember our math from earlier? Tan delta relies on that ratio between viscous flow and elastic bounce. The Vitrimer core provides that high viscosity you need to dissipate shock energy. Normally, at high temperatures, a Vitrimer would just get too soft and lose its shape. But those outer elastic spandex layers step in to provide the structural bounce, holding the whole thing together. By bouncing these properties out, they essentially hack the material to artificially generate that elusive, broad tan delta plateau. And the results of this composite sandwich, absolutely phenomenal. When you look at the DMA testing now, you don't see that sharp, narrow peak anymore. Instead, you get an incredibly stable, flat damping plateau, spanning from 20 degrees all the way up to 90 degrees Celsius. That's a 70-degree operating window where the material provides stellar, unwavering vibration damping. For mechanical engineering, that is an absolutely huge win.
All right, let's pivot to our final segment, Section 5, additive manufacturing breakthroughs.
We all know 3D printing has changed the world, right? But it still has a huge Achilles heel, and that is gravity. If you try to 3D print using a vat of liquid photoresin or a bed of fine powder on, say, a turbulence-hit airplane, a rocking naval ship, or a zero-gravity space station, you're going to have a massive, unworkable disaster. The liquid sloshes around, the powder floats away. To print in harsh environments like that, we desperately need a way to 3D print using a completely solid-state material. Enter a very specific, highly functionalized Vitrimer-like polymer. It's called UPY-STPB-UPY. Yeah, I know, it's a bit of a mouthful, but here's the magic behind it. It uses strong, quadrupolar hydrogen bonding to act completely solid at room temperature. But embedded right there within its chemical backbone are these unsaturated double bonds that are basically spring-loaded. They are chemically primed and ready to be permanently locked into place the very second they're hit with ultraviolet light. And because of that unique chemistry, it unlocks this wild three-step workflow called solid-state volumetric additive manufacturing. Here's how it works. Step 1, you take a completely solid, dry block of this Vitrimer material. No liquids, zero mess. Step 2, you project a 3D hologram of UV light directly into that solid block. Wherever the UV light hits, the material instantly cross-links and becomes permanent. Step 3, you just wash the block in a mild solvent. All the uncross-linked Vitrimer safely dissolves away, leaving you with your perfectly printed, high-strength part. The really crucial detail here is that this UV exposure isn't just carving a shape out of a block. It's actually inducing a chemical reaction that permanently upgrades the part itself. It shifts those targeted areas from a reshapeable thermoplastic into a tough, permanent thermoset. The data shows this greatly enhances the material's fracture strain and tensile strength. Plus, because of the Vitrimer's native shape memory effect, the final printed part keeps incredible dimensional accuracy, meaning it resists warping and shrinkage like a champ. As the researchers explicitly pointed out, taking this solid-state Vitrimer approach completely removes gravity, motion, and stability from the additive manufacturing equation. Think about what that means. An astronaut on a tumbling spacecraft could literally pull a solid block of polymer out of a storage bin and instantly 3D print a replacement wrench, or maybe a custom medical splint, literally anywhere in the universe. I really hope this explainer has shown you the absolute incredible potential of Vitrimers. By blurring that line between plastics and rubbers and letting us tailor their dynamic chemistry, we've engineered materials that can heal themselves, absorb massive mechanical shocks over huge temperature ranges, and actually allow us to 3D print in the vacuum of space. It really leaves us all to wonder. As this technology scales up, what impossible engineering challenge will these shape-shifting superpolymers solve next? Thanks so much for joining me on this deep dive, and keep learning.